In this video, we propose a formation navigation framework for heterogeneous robots. Some recent work has proposed methods for formation navigation. However, these methods still have their shortcomings. They either don't fully consider formation constraints, can't ensure both formation integrity and collision-free navigation at the same time, or only work with homogeneous robots. To address the above issues, our work proposes three key solutions. We propose a unified distributed framework for heterogeneous robots that integrates a convex polygon-based multidimensional formation control scheme with a desired state-driven trajectory planning method to achieve robust and scalable, adaptive, collision-free formation navigation. Motivated by the previous research, we present a navigation framework that integrates formation maintenance and collision avoidance. Our framework consists of two components: formation-level configuration planning and agent-level trajectory planning. Here, we geometrically describe the desired formation by constructing a virtual convex polygon, and the robot's positions can be represented by linear combinations of the polygon's vertices. When the formation deforms, the vertex set of the virtual polygon adjusts dynamically, and the robot's positions are updated synchronously via the same affine transformation. This video demonstrates the actual operation effect of our method. For the distributed single robot trajectory optimization part, first, based on the initial formation guidance state, a kinematic A-star algorithm combined with topological homotopy technology is used to generate the robot's front-end path under non-fully constrained kinematic constraints. Then, a graph similarity-based method is adopted to construct a soft constraint optimization problem, thereby generating the robot's back-end trajectory. This video shows the single robot trajectory optimization effect, where the red curve is the finally optimized trajectory. In the simulation experiments, we set up three scenarios with different obstacle densities. The first one is a formation navigation test with 5 robots in a 50-meter by 50-meter medium density area. The maximum speed of each robot is limited to 1.5 meters per second, and the acceleration is limited to 1 meter per second squared. We compared the proposed algorithm, and in the same scenario, MDSFGS demonstrated better formation maintenance rate and real-time performance. The second experiment is set in a high obstacle density scenario, with all other configurations the same as those in experiment 1. In this scenario, we conducted multiple experiments, and the proposed algorithm consistently maintained a high formation maintenance rate, high success rate, and good real-time performance. As we can see, NUN-FGS combines virtual structure and artificial potential field methods to maintain formation and avoid obstacles. However, because it does not pre-plan the overall formation state, robots tend to prioritize their own safety, leading to poor formation keeping capabilities. DRRT-FGS relies on random sampling to find suitable positions and scales for the formation, but it only considers these two factors, often causing it to deviate from the planned state during execution. SCFGS constructs a continuous convex safe corridor for the formation, but this results in extended trajectories and excessive time costs, which limits its real-time performance. To validate the method's scalability, we deployed 15 robots in a circular formation for scenario 3. During navigation, the formation adjusted its shape in real time and maintained consistent coherence, with no deviations observed. As shown in the table are the final simulation results under different obstacle densities. The evaluation metrics include formation similarity, formation maintenance success rate, formation trajectory length, and trajectory planning time. We tested our method works in real environments, and here we used 3 different types of ground mobile robots. The first experiment shows an open area filled with obstacles, where each robot needs to maintain the desired triangular formation while avoiding obstacles. We can see that robots adjust formation quickly to avoid obstacles in obstacle-rich areas, and formation similarity recovers quickly in open areas. Experiment 2 is conducted in a narrow corridor environment, where the overall formation planning needs to accomplish a 90-degree right-angle turn. We can see that when robots navigate sharp, narrow corners, the formation adjusts rapidly, leading to a temporary drop in similarity. After exiting, it quickly reverts to the desired configuration with high similarity restored. Thanks for watching.